So from Price, her tip here, or a couple of tips, editing seems to occasionally corrupt MXDs, your map documents. So on the previous slide, I mentioned it's a good idea to edit in a new map document, a new MXD, just one used for that purpose, using only the minimum number of files that you need at that time for editing, and then save your work as you go. Maintain a backup copy. And her last bullet point here is really important. If you've been working on a map for a long time, that is not the MXD that you want to be working in when you're editing data. Because if that MXD gets corrupted and it's gone, all the work that's stored within it is gone. Your data sets may be fine, but the MXD itself will be lost, or can be lost if there's an editing hiccup of some kind. So again, edit in a new MXD, a new map document that's separate from the major work you're doing on a project if you're creating maps for that project. So a little bit of review again about terminology. Points, lines, and polygons are vector features, whether they're stored in a feature class in a geodatabase or a shapefile or a coverage that exists outside of a geodatabase. Since most of the work in the class exercises focuses on using geodatabase datasets, this slide is focusing on that too. So ArcGIS feature classes are a collection of features, all of the same type, the same projection. So each feature class is either all points or all lines or all polygons, and that data set, all of those features share the same attributes, the same variables, which are basically the columns in the table. So that relates to features. Okay. A feature data set is a collection of feature classes. They all have to have the same projection. You can mix and match points, lines, and polygons. They can have multiple attribute tables. So it's like putting all of the data for a county together in a feature data set. All of the point, line, and polygon feature classes are stored together as a feature data set. Okay, so and remember that these are related to geodatabases. So feature classes and feature data sets occur within geodatabases. If you have vector data exterior outside of a geodatabase, it will most likely be either a shapefile or a coverage, which are older data formats. Within a geodatabase, an individual data set that's in vector data model is known as a feature class, and the individual features are the rows in a table, and the attributes are the columns in a table. So this would be an example of a feature class being the states in the United States, and we're showing 3 states, Washington, Idaho, and Oregon, as individual features, and then the attributes are the columns. So information about the states are in the columns. And that's what a feature class is from the user perspective. Feature classes work pretty much the same way as shape files. They're virtually interchangeable. There are some advantages to using feature classes that we'll see later on. But as far as the data contained within them, they're very similar to each other. They work pretty much the same way. So a feature class will work as a shapefile. You can export a feature class as a shapefile. You can import a shapefile to create a feature class. And feature classes occur within geodatabases. Shapefiles or coverages occur outside of geodatabases. Feature data sets are again collections of feature classes that share an identical common projection system. So here's an example from a data set used in an exercise of a feature data set, which has its own icon in ArcCatalog, and then underneath it you see the individual feature classes. In this case, it's a city with fire hydrants, parcels, water lines, water valves. So 2-point location feature classes, a polygon feature class, a line feature class, collectively a feature data set. We can further break down the vector data model into these two major approaches: georelational vector data model and object-based vector data model. Georelational are the older versions. Coverages and shapefiles are typical ones that you will encounter in work today. Object-based would be things stored within geodatabases, whether they're personal or file geodatabases or server-based ArcSDE geodatabases. So what are these two different distinctions? Georelational data is spatial and attribute information stored in separate files on the hard drive, and they're linked together through a key field in the table, usually the ID or the object ID field or attribute in the table. So we store the spatial information in a file by itself, the attribute data related to that data set stored in a separate file, but the system links them together through that key field. So essentially it's loading up two tables at once. It links them together in memory as you use the data set. Object-based models are where we store spatial and attribute together within a geodatabase, and that enhances the things that we can do with regard to the relationships between them and the kinds of analysis that can be done. So these are objects that have geometric integration with other features in the data set, whether it's point, line, polygon, network, annotations, whatever you're working with. Geodatabases are a little bit more powerful to use with regard to the types of things that we can do and how we can relate and make relationships between the different types of data. Here's an example of a shapefile showing Washington, Oregon, and Idaho. As it looks in our catalog, it's a single icon with an extension. If you look at it in Windows File Explorer, you'll notice that the shapefile is comprised of multiple individual files stored on the hard drive, and they all serve different purposes: attribute information, spatial information, the metadata, the projection parameters, an index file, and the data lock, meaning that that particular shapefile is open somewhere in ArcGIS, whether it's ArcCatalog, ArcMap, ArcGlobe, or ArcScene, whatever. It's open someplace, and you're not going to be able to edit it, basically, is what the lock will do. Okay, so anyway, what this is showing us is, here's the example of the information being stored in different subfiles physically on the hard drive, although we see it as one file in the ArcCatalog File Explorer. An older version of vector data is the coverage. Coverages store things in two different folders: the name of the coverage and an info directory. It needs both of those. And within the different directories, you're going to find a lot of files together with different extensions, different names. You're not necessarily going to know what those things are. But for example, here we've got 4 different file extensions. The dir tracks file pairs of nits and dats for each ADF. ADFs are Arc data feature classes related to a pair of .nets and .dats. .nits are info table definitions. Info is a type of a table, like an Excel table, but it's a different architecture. .dat, for example, is a feature attribute table. So there's a lot of information that's stored in those things in ArcCatalog. On the left in the diagram, you'll see that there's an icon for the coverage that's different from feature classes and from shapefiles. and that the difference is there to visually show you this is a coverage, and it's comprised of these different sub files that can be accessed from our catalog and modified and edited. Okay, so it's a little bit more of an odd structure compared to the ones you've been using, shapefiles and feature classes. But anyway, so here's what that looks like. Switching over to the object-based or object-oriented vector model, a personal geodatabase in ArcGIS is designated by the extension MDB. It has that particular icon associated with it, and you got feature data sets, feature classes within it. It has a lot of tables related to it. In ArcGIS, you're not necessarily going to see those in the Arc catalog structure. We have a lot of information for, well, what we can do is, we can store a lot of information in geodatabases, thousands of records, thousands of attributes, in some cases much more than that. Personal geodatabases are things that I would recommend you do not use. They can store 2 gigabytes maximum of data, but what we've noticed in reality is that about when they get to 250 to 500 megabytes in size, we start seeing the personal geodatabase degrade, which means file errors, computation errors, and outright failure of the geodatabase. It's all stored within a single file structure on the hard drive, and it's more easily corrupted. And so from that, my strong suggestion would be never use a personal geodatabase, even though they exist. Instead, I would highly recommend that you use a file geodatabase designated by the extension .gdb. The icon looks very similar to a personal geodatabase, but the extension will tell you it's a file geodatabase. File geodatabases have a maximum capability of storing 1 terabyte of information. Hundreds of millions of vector features can be stored in them. Each data set is separated within the storage structure. So if one data set goes bad, you should still be able to use the entire geodatabase or the remaining portions of the geodatabase. So it's a better container, basically, within which to store data if you're going to be using geodatabases. It's more robust and more prone to survival when corruption occurs. So anyway, this is what I would recommend you use. These are the ones that we use throughout the class. Whenever you create a new geodatabase, create a file geodatabase. It'll save you a lot of headache down the road. So how can we get different tables to talk to each other within a GIS structure? Those are what we call relational databases, or databases that are related to one another. And here we've got, from our secondary textbook, some examples of 4 tables with different pieces of information, different names, and different attributes, but we wanted to get these things together. So is it even possible to link these things together? So we've got our tables, which you can think of as each table being an individual feature class or an individual shapefile. It has its own characteristics on it, or attributes stored within it. And we have different tables, and these are small ones, with information about the same areas. Okay, and so we want to try to get those different things together. The columns are also known as fields. Those are our attributes or variables. And again, remember that the individual rows are known as records or features for these different tables. Where the linking starts is that we need to have a table that has a primary key uniquely identifying each row, each record, each feature within the feature class or shapefile. So in this case, we're going to have forests as the main table we're trying to work with, and we have a primary key, which is the forest ID. Each forest has a name, but each one has a unique identifier, the number, 1 or 2. In this case, a very short table with those two forest names, but we've got that primary key, an ID number that we use to uniquely identify each of those two forests. The primary key then gets used, or it can be used, in other tables that contain it. Okay, so in this case, the primary key is called forest ID. The label doesn't really matter as long as the number in it, the code, means the same thing in other tables wherever it occurs. But in our first table, it's the primary key. If it's another table like trails that we're trying to join and link to the forests table, it has a foreign key. Okay, our table we're trying to bring in is known as a foreign table. It has a foreign key with the forest ID, although the label could be anything, doesn't really matter. But the ones and the twos in the trails table refer to Nantahala or Cherokee forests. So when we join these things together, we literally are pulling in the trails information and adding it and creating a new table that's comprised of all the information from forests and trails. So this is an example of a joined table on the bottom where the information from the forests table, which is the Nantahala and Cherokee forests located in North Carolina, and the sizes of them, think of that maybe as square miles, 184,000 square miles, 92,000 square miles. It could be acres, doesn't really matter what that is. And from the trails table, we have trail names and the forest ID. So the combined table shows us forest name, forest ID, the location, the size, and then the trails that are located within each forest. So we've joined the information together in GIS, and we can join lots of tables together in sequence to compile a large data table for whatever our original table was, related information related to that. So here's another example using FIPS codes. If we have FIPS codes in common between the tables, FIPS is a numbering sequence used by the U.S. Census. We've got our destination table or our original table. We've got a source, the one that we're bringing information from. We join those things together, and we wind up with a table that has, again, the information from both. So our destination table, or our original, has the primary key of FIPS. The source table we're bringing information from has that same FIPS column, although we don't see it on the graphic. Those numbers are going to be identical between them, and they're going to mean they're going to relate to the same features, which is U.S. counties. So one thing to take away from this particular slide is that it doesn't matter if they're ordered the same or not in each table, as long as the numbers match. If the numbers match, the information from the source table will be brought in and appended directly to the matching number on the destination table. And then we wind up again with a joined table containing information from both. So our original table, our first one for U.S. counties, has object numbers, the shapes, the name of the counties, the state name where they're from, and the FIPS code is the unique identifier. And that's all we have in there, but we want to bring in more information from the census. So different measurements made at the county level at different points in time. In this case, we're looking at the population of each county in 3 years: 2002, 2001, 2000. And the joint table just does that. It brings it in, and then we've got that information for each county in the U.S. Linked together by the common FIPS codes.